Yeah, thanks for the introduction. And yeah, first of all, I'd like to thank the organizers for the very kind invitation. It's a great honor to give this talk today. And it's also been a great week. I've enjoyed a lot so far. Hopefully we don't ruin it with the last couple of talks, but it's been very enjoyable. Yeah, a really nice group of people. So yeah, many thanks. And today I'd like to discuss a recent, well, not so recent result in collaboration with Christoph Boom from Münster. And it's about Einstein manifolds with symmetry. So please, I've written very few slides. I mean, only 13, 14 real slides. So this is to allow time for questions. So please do interrupt me if you think something's not clear. But let's start by explaining the words on the title. So in this talk, I'll be working with a complete Riemannian manifold, and we call it Einstein if the Ricci tensor is a multiple of the metric. Right? Now, this is a very complicated equation. It's a nonlinear PDE. In certain coordinates, you can see it for the metric entries as a kind of Laplace equation or Poisson equation, but there's some lower order terms which are nonlinear. And I'll be interested in the case where the lambda, then the Einstein constant, is negative. So in particular, up to scaling, we can normalize it to be -1, just so that it doesn't bother us. And I will do so for the rest of the talk. So I will not discuss the Ricci flat case or the positive Einstein constant case at all. Right. So let me mention some examples of Einstein manifolds. The first examples are very well known, of course. Perhaps the most well-known Riemannian manifolds after the space forms are the symmetric spaces, right? So in a reducible symmetric space, in this case of the non-compact type, because I want negative constant, is automatically an Einstein Riemannian manifold. They were classified by Cartan. Here, there are some examples. So you have, for instance, the rank 1, some of the rank 1 symmetric spaces, and then some more complicated, it's a semi-simple, non-compact semi-simple D group mod the maximal compact. If the group is simple, this always admits a unique homogeneous metric, and it is Einstein. And by result by Borel, they all admit compact quotients by discrete group of isometries. So this gives example of compact Einstein manifolds of negative curvatures. These are all locally symmetric, of course. Then some examples from analysis, right? So the previous examples were coming essentially from algebra. You classify semi-simple algebras to understand these objects. But from analysis, so in the 70s, Aubin and Yau independently solved the Monge-Ampere equation, and they could prove the existence of Einstein metrics on some compact scalar manifolds, right? So the technical condition is you need to require this topological assumption that the first Chern class is negative definite. And then within the given Keller class, there exists a unique representative, which is an Einstein metric. So this is an extremely beautiful result. Then this was generalized to the case of 0, first Chern class, even more famous than this one. And this provides a lot of examples, right? Which have no symmetry actually, or no continuous symmetries. So we won't be looking at this during this talk, but it's a very important set of examples. You see, right? So many years have passed until we get the new set of examples, 29 and then 76. Then the new set of compact examples came much later, actually. And these are due by to Anderson. And then there were some issues in this paper fixed by Richard Bamler in 2012. And there's a very recent paper by Joel Fine and Premoselli in 2020, where they construct new examples of compact Einstein manifold. All these constructions are very complicated, but they are all related somehow to hyperbolic manifolds. I don't want to say too much about this. Now, these are not only some examples. In the compact cases are all known examples, as far as I know. So to discuss a bit more richer class of example, I will move on to the non-compact case, okay? And this brings the second word in my title, which is symmetry, right? So what do I mean by symmetry? Well, I mean something very precise. And the setup is the same. We have a complete Riemannian manifold, which is Einstein. And by symmetry, we assume there's a connected Lie group which acts by isometries, meaning there's a Lie group homomorphism from G into the isometry group of the manifold. It acts properly. This is a technical condition because our groups could be non-compact. So if you want to have nice properties, you need to assume this, but this is not important. You can always close the image of G in the isometry group and you get a proper action. And this is a key assumption, which is by no means natural, but well, theorems have assumptions and this is ours, right? We assume that the quotient by the G action is a compact topological space. It's a compact metric space, in fact. Okay. So maybe some immediate observation under these assumptions, because the Ricci curvature is negative, there's a not so well-known result by Bochner that for a compact manifold with negative Ricci curvature, the dimension of the isometry group is 0. There are no killing fields on these manifolds. And you can prove it using a Weitenbach formula for killing fields. But therefore, the manifold has to be non-compact. And in particular, because the quotient is compact, this implies that G itself is a non-compact Lie group. Okay, so we'll be talking about non-compact Lie groups. And perhaps I should give you some examples of Einstein metrics which satisfy these seemingly restrictive symmetry assumptions, right? And the simplest set of examples is given by the case where the quotient is a point, namely the action by G is transitive. These are called homogeneous Riemannian manifolds. So in this case, I've already mentioned symmetric spaces, and we have a call in the room, but hopefully it's not for me. But let me mention some non-symmetric examples, right? So the first non-symmetric homogeneous Einstein manifolds of negative scalar curvature are these so-called Einstein solved manifolds, right? So this is a fancy name for some very simple object. It's a solvable Lie group, which is simply connected, and it has a left invariant metric, which happens to be Einstein, okay? So the person who discovered the first classes of examples in this setup was Dmitry Alexievsky, and in the context of quaternionic scalar geometry, right? So these are actually the first non-symmetric examples with holonomy, with quaternionic holonomy, and therefore by properties of this type of special holonomy, they're automatically Einstein. And then they were studied by a number of people. I couldn't mention everyone. Maybe I just decided to mention the most important papers. So this classification of this quaternionic scalar Einstein solved manifold was completed by Vicente Cortés. And then without the quaternionic scalar assumption, just purely studying the Einstein equation on left invariant metrics on solvable Lie groups, there's a seminal paper by Jens Heber in Invenciones, 70 pages, and he does a lot of results, very interesting results. Like if there's such metric, then it's unique up to isometry, and then he studies the moduli space using techniques from algebraic geometry. It's an extremely interesting paper, which I read many times. And there's some newer results by Lauret and Jablonski more recently. Now, the main question about these homogeneous Einstein manifolds of negative scalar curvature was this conjecture by Dmitry in 75, which says the following. So, I mean, a solvable Lie group which is simply connected. It's an exercise in this theory. You can prove that the manifold, the underlying manifold, is Rn. You can prove it by induction, right? Now, the question is, if you have a homogeneous Einstein space with negative scalar curvature connected, of course, everything is connected, then does it have to be diffeomorphic to Rn, or can it have non-trivial topology, so to speak? So this is called the Alexievsky conjecture, and it's been open since 75. And so the main result I want to present today is a solution to this in collaboration with Christoph Böhm last year. This is true, okay? So any homogeneous Einstein space with negative scalar curvature as a manifold must be diffeomorphic to Rn. Of course, the metric will be very far from the metric in Euclidean space, right? But and moreover, up to isometry, it's one of these Einstein solved manifolds. So this last part is actually a remark. I mean, it's much easier to see. The main thing is that it has trivial topology. Okay, and of course I should mention all the people that worked on this problem, and there's a very long list. Unfortunately, because I don't want to make this a survey talk, I want to point into the direction of this very recent survey. So you can zoom in with your phone and just click on the QR code. And yeah, Mike Jablonski wrote this beautiful survey last year. So I would recommend you to check it out. But yeah, perhaps it's a good time to ask, are there any questions about the statement of the theorem, the conjecture? Does this even work? This was the first time I tried this, but it worked on the computer at least. I wonder whether it's large enough. It's an archive paper. Yeah, great. Yeah, very beautiful survey. Not only about the non-compact case, but also the compact case. Okay, so I mean, the main goal of my talk is to try and explain some of the ingredients in the proof of this theorem. So the paper is a bit technical, but hopefully by hiding some of the technical details, I'll try to explain what are the main ideas involved in the proofs. So let's move into that then, if there are no more questions. Yes, I go back to the survey. Yes. I mean, in this case, yes, in principle, but because the metric is homogeneous, the answer is no, because it will become clear in a minute why not. By homogeneity, you only care about what happens at one point, actually. It will not decay at any rate because it's homogeneous, so you can say it's constant morally, right? So any curvature invariant will be constant along any scalar curvature invariant will be constant. So there's no decay. So from an analytic point of view, it's a strange problem. Yes, I agree. But there's so much symmetry that you can use algebra, maybe. That's actually one of the key points in the talk, right? Whether you use analysis or algebra to study this question. So maybe some remarks before I start. So the theorem is I have a homogeneous space, which for some strange reason that will become clear in a minute, I call the transitive group F. And so this is F mod H, homogeneous space, Einstein, then we have to prove that it's diffeomorphic to Rn. So what does this mean in terms of Lie theory? Well, there is always a maximal compact subgroup containing any given compact group, subgroup H. We call it maximal K. And then it can be seen that M is homotopy equivalent to K mod H. So the topology of a homogeneous Riemannian manifold is the topology up to homotopy equivalence is it's a compact homogeneous space, right? So to prove this, you have to prove that, I mean, it doesn't immediately follow, but you can see this, that you have to prove that the maximal compact subgroup is the isotropy, okay? So coming back to your question, I mean, the homogeneous Einstein equation, it's a PDE, but by symmetries, the derivatives disappear, right? So you can write it as a set, very complicated set of polynomial equations. These are quadratic polynomials on the structure coefficients of the Lie algebra. And that's it. That's the equation. And you can try to solve it, put it on the computer, and spoiler alert, I mean, it gets very complicated pretty quickly. In dimension 5 and 6, it's already much for a computer, at least a non-quantum computer. So, but that's it, right? It's an algebraic equation. And now, what are some of the key properties? Well, I mean, I don't want to give too many details, but I want to communicate the fact that to me, the problem with this algebraic equation is that when the group is semi-simple, right, here the structure constants of the Lie bracket appear, right? So the Lie theory of F will be crucial in studying the equation. And when it's semi-simple, we understand very little of this equation. Namely, nothing. I mean, it's just a bunch of polynomial equations that could come out of nowhere, right? And maybe to justify this, up to this point, we didn't even know whether this seemingly innocent 6-dimensional Lie group SL2C had a left invariant Einstein metric or not. This is 6 dimension, right? So the metric is a 6 by 6 matrix on a vector space, and then you can write down the equation. It depends on, I don't know how many 6 choose 2, no, maybe more variables, but if the conjecture were true, well, it is true, then because the topology is non-trivial, because the maximal compact subgroup is SU2, it should not have solutions to the Einstein equation, right? But this was open even for this case. Now, on the other hand, there's the fact that in the solvable case, we have very good understanding, not due to me or Christoph, but due to all the people that I mentioned in the previous slide. In particular, these 2 papers by Jens Hieber and by Jorge Lauret in 2010. So the idea is try to use this very good understanding in the solvable case and then do something about the semi-simple part, right? So perhaps the key point is you want to study this equation by forgetting that the manifold is homogeneous. So then again, coming back to your question, we're gonna forget that the metric is constant. We only look at certain non-transitive symmetries, and then there's a disadvantage, of course. You get a PDE instead of an algebraic equation, but that's the price you have to pay. So we're gonna study the Einstein equation under a non-transitive group. Okay, this doesn't seem like a very good idea, but it is so because of these 2 observations, I mean, vague observations that I wrote there, right? So more precisely, what do I mean by that? For simplicity, let's assume that H is trivial and F is a semi-simple Lie group, say SLMR. Okay, so that everyone understands what we're talking about. I don't want to be super technical in Lie theory. Of course, the general proof will need a little bit of technicalities, but this is not important. So topologically, this Lie group is SOM cross some Euclidean space. Therefore, it should not have an Einstein metric which is left invariant, because what the conjecture said, it has to be diffeomorphic to Euclidean space. Right? So we must show there's no solution. So the idea is you look at the Iwasawa decomposition, right? KAN. Here K is SOM, and AN, I call it G. That's why F was a transitive group. I want G. This is the main character of the proof, not character in the sense of representation theory, but the star. And in this case, it's very explicit, right? The set of upper triangular matrices with positive diagonal elements, the Borel subgroup. And instead of looking at the Einstein equation as a left invariant metric on SLMR, we only use the fact that G acts by isometries on this Riemannian manifold. Okay. Which seems a bit stupid because you had so many symmetries and you are throwing them away, most of them, right? But again, the fact that it's solvable and the fact that we understand Ricci curvature in the solvable case much better, that's what's behind this idea. So we get what it's called the principal bundle, because the action of G is free, right? Nothing fixes anything except for the identity. Then just by definition, this is a G principal bundle. Topologically is trivial, but metrically is highly non-trivial, right? Namely, well, then we're gonna study the Einstein equation for principal bundles. And more general, in the paper, we study the Einstein equation for non-transitive group actions, not necessarily free actions, but let's just assume, I mean, that it's free. So the drawback is, of course, well, now we are back to a PDE, right? It was an algebraic equation, now it's a PDE with some algebra, but you gain something because the PDE actually happens on a compact manifold. Because if you notice, the quotient by the Borel is gonna be diffeomorphic to SOM. And this is completely general by the Iwasawa decomposition, right? So then hopefully, you know, PDE on non-compact manifold, you don't want to do that, right? I mean, I'm not able to do that, but on a compact manifold, maybe you have maximum principles, you have, maybe there's some hope to do something. And then, of course, algebraic data coming from the G orbits, which will play a role, right? Okay, so if you don't like homogeneous spaces, you can forget about the first 6 slides. And now I will talk about the Einstein equation on principal bundles. Right? So in principle, this is totally disconnected from the previous talk. So this is the case of symmetry where the general case, I mean, the quotient is not a point, it can be any compact metric space a priori. Well, in this case, the quotient is a manifold because I'm assuming that the action is free. And so that's the setup. And this is a G principal bundle. And then we have what's called the Riemannian submersion, right? So the metric on M, because it's G invariant, it induces a metric on the quotient, the so-called quotient metric. This is very well known, right? And so that this projection is a Riemannian submersion. So what do I mean by that? Well, here you have the G orbits. This is M, right? So you have the G orbits. G is non-compact, so that's why the picture is like that. And as I said, projection to some compact base B, and then on the infinitesimal level, you have, I mean, a distribution given by the tangent spaces to these orbits. The orbits are submanifold, so they have tangent spaces. This gives you a distribution which is called the vertical distribution, right? But we also have a metric on M, so you can look at the orthogonal complement of the vertical distribution. Let's call that the horizontal distribution, and then you copy the metric from the horizontal spaces to the tangent space of B, and that gives you a metric on the quotient, so that this pi, by definition, will be a Riemannian submersion, right? So now let me tell you how to recognize, I mean, how to encode the G invariant metric in this setting of Riemannian submersions, right? So what objects you need to care about? Well, first of all, the restriction to each one of the orbits is going to be a G invariant metric on the orbit, right? But the orbit is G. I mean, it's not G because there's no identity. But if you fix a point, it's G, right? So each orbit is like Riemannianly like a left invariant metric on G, okay? So you have a family of left invariant metrics on G, which is indexed by the base manifold. Then you also have to remember what's this V plus H decomposition, because for that we use the metric, right? So in the theory of principal bundles, choosing such a complement to the given vertical distribution is called a principal connection, right? Maybe you've seen connections as one forms with values in the Lie algebra. This is exactly the same. H is the kernel of that one form. And finally, we need to know a Riemannian metric on B, right? So conversely, given this data, you can cook up a G invariant metric on M, okay? So now the Einstein equation will become a set of coupled equations for these objects here, right? So let me try to, okay, one thing is locally, at least, you can view this, this G hat, right? The family of metrics on the orbits. I mean, if you fix a point, then the tangent space to the orbit is the Lie algebra of the group, essentially, right? So you can view this map as a map from the base to inner products on the Lie algebra, which one could parameterize by this symmetric space GL mod SO. Maybe I need to put a plus, I don't know, but essentially this is what you have, right? So G hat is a family of inner products on a Lie algebra indexed by the base manifold, right? So to present the second main result, so the result in the context of Einstein principal bundles, I need to tell you a little bit more, namely this notion of the nil radical of the Lie group. I hope many of you will know this, but I usually have to explain it for different audiences because this is not so well known outside of Lie theory. It's a maximal connected nilpotent normal subgroup. For instance, if you have SL3R and you pick the Borel G, then the nil radical of this G is the Heisenberg group. Okay. Now the nil radical of SL3R is trivial because G is semi-simple, but the nil radical of G is the Heisenberg. Okay. All right. So let me tell you what's the main result in the context of principal bundles. So let's let M G be a G principal bundle. I mean, meaning the action of G is by isometries and the quotient is compact. Then if it's Einstein, if you look at the corresponding principal bundle for the nil radical action, I mean, G acts on M, but M is a subgroup of G. Therefore, N also acts freely. Therefore, you also have a principal bundle for the N action. Okay. Now the result is about some properties of this smaller, I mean, less interesting principal bundle. And we have the following. So the Einstein equation forces the following facts. Firstly, that the horizontal distribution of the N action is integrable. Now the vertical distribution is always integrable because the integrals and manifolds are the orbits. The horizontal need not be integrable. This is equivalent to saying that the principal connection is flat. Or also, we had many talks this week about this concept that the N action is polar. So the N action is polar. Secondly, the geometry of the orbit is very well understood, namely, they are Ricci solitons. Nil solitons, one would call them, because these are Thm B metrics or nilpotently groups, which happen to be Ricci solitons. So this is a slight linearization of the concept of Einstein metric, which appeared in Ricci flow theory. And thirdly, this map from the base into inner products on the Lie algebra is a harmonic map between Riemannian manifolds. Okay, so you have these three now PDEs. Well, this one is actually a family. I mean, because I'm saying all the orbits are Ricci solitons. They're actually pairwise isometric, in fact, but this is not important here. But so you get, and this is like a Yang-Mills. I mean, it's a flat connection, right? So the Einstein equation implies the connection is flat, the orbits are solitons, and this metric on the fibers gives you a harmonic map. Okay, so it implies non-trivial properties for all these ingredients of that I mentioned in the previous. So maybe if you're familiar with the theory of Einstein solved manifold, if you restrict to the homogeneous case and you suppose that G is in addition solvable, then the first item is equivalent to the fact that Einstein solved manifolds are standards. Okay, this was a celebrated result by Lauret, published in the Annals. So in the homogeneous solvable case, this is what item 1 means. Right? But of course, we are interested in the non-transitive case. All right. Any questions about the statement, theorem 2? Well, if it's not the case, and some are still following, maybe I will try to say a few words about how to prove this. What's the main idea? So that's the theorem again. So when you have a Riemannian submersion, then you can understand the curvature in terms of the curvature of this family of metrics on the orbits, the curvature of the metric downstairs, and two tensors defined by O'Neill in the 50s, which I call A and T. Now, unfortunately, this A is not the A that they use in physics, namely A is for connection in physics, but here A would be like the curvature of the connection. This is unfortunate notation problem, but that's the way it is. These are the two tensors that you need to care about. Namely, the first one measures the integrability of the horizontal distribution. So X and Y are horizontal vector fields. U and V are vertical vector fields. And the second, the T, is simply you collect all the second fundamental forms of the orbits. The orbits are submanifolds. Each submanifold has a second fundamental form, but you have a foliation by these submanifolds. Well, this gives you a tensor of type 1, 2, and this is the definition. Right? So in terms of these two tensors, well, you also need to know the mean curvature vector, which is some sort of trace of the second fundamental form. In the case of a principal bundle, you can write it as a gradient vector field where the potential is the logarithm of the volume density of the orbits. So here UI are just a fixed frame of Killing fields spanning, the vertical distribution, and then you write the metric vertically in these coordinates and this frame, sorry, And that gives you a potential for the mean curvature vector, right? It's just the same. So then the Einstein equation becomes, together with n invariants, becomes a set of PDEs. I mean, the first one corresponds to the vertical part. I mean, Ricci you should think of as a matrix, right? As a vertical, horizontal. So there's a 2x2 block matrix. This is a vertical part. This is a off diagonal one, and this is a horizontal one. I don't want to tell you this because I won't use them, but just let me give you a try to explain what's the vertical Einstein equation. So the first, so here Ij correspond to vertical coordinate, and the alpha corresponds to a horizontal coordinate. So first of all, you see this this is like the Ricci-Soliton equation. I mean, there's a Ricci of the orbits, delta Ij, and then there's this term which is kind of a Lie derivative of the metric. So this orange part will correspond, the vanishing of this will correspond to the orbits being Ricci-Solitons, which is part of what we have to prove. Now, the last one is just a positive term. I mean, this is an endomorphism of the vertical distribution, but it's a positive definite, and its trace is the norm of A squared, right? So if you prove that this vanishes, then you're proving that H is integral, which is another one of the items, right? And finally, the stuff in between is when it equals 0, this means that the map G hat is a harmonic map. Okay, so you have all these 3 PDEs, but they are combined into one equation. So we want to show that each one of these 3 terms vanishes. Okay. Yeah, this is a bit technical, but it's what it is, right? So let me mention, I mean, people have looked at the Einstein equation, or in general, Ricci curvature under this symmetry, you know, where the symmetry has a compact quotient. So in particular, there's a paper by Sheshung Rong in Duke in '98, where he deals with the Ricci negative case, in the case where the group is abelian. And then there's a more recent paper by Neighbor and Tian, where they look at the Ricci flat case for nilpotent symmetry. I mean, the reason people, there's also a paper by John Lott, a very important one on the Ricci flat case where G is abelian. And the reason people look into this is because there's another motivation for looking at the Einstein equation with symmetries, namely collapsing with bounded curvature. When you have Riemannian manifolds that collapse with bounded curvature, they acquire symmetries asymptotically, and the symmetries are coming from a nilpotent Lie group essentially. So that's the reason why people care about this equation with nilpotent symmetries. And what, I mean, this is not the main statement in their papers, but at the end of the day, the core of the arguments for the results that they prove, it involves the following. They want to prove some rigidity for these spaces. So they look at the volume density of the orbits, right? This the potential of the mean curvature vector that I mentioned, right? Square root of the determinant Gij. That's a function on the orbits. It's of course n invariant because everything is n invariant. So it's a function on the quotient. It's actually G invariant in this case because for them G is equal to n. So it's a function on a compact manifold which satisfies a very nice differential inequality, namely the Laplacian plus some first order term. There exists x such that this holds. Okay, this is not for all x, of course, but this doesn't matter because I mean you can apply the maximum principle here because M mod G is compact, and if you have such a differential inequality, this implies immediately that the function is constant by the maximum principle. And therefore, you have equality here, and this is the important piece of information, because to prove this equality, you used the Einstein equation, right? You use estimates, you threw away things. So that's how you gain information out of such a differential inequality, okay? So the idea is we try to do the same for our equation, okay? Try to use this volume density, but there's 2 issues, and they are unfortunately very important. Namely, for us, n is not abelian. Therefore, in the vertical Einstein equation, the Ricci curvature of the orbits appears, and it appears and it hurts you. I mean, it's with the wrong sign, so to speak. So in the abelian case, the orbits are flat because they are homogeneous spaces of an abelian Lie group, right? But in this case, there will be curvature of the orbits. And because our group G is non-unimodular, then unfortunately, the volume density of the n orbits will not be a G invariant function. Remember, G is the Borel, n is the nil radical of the Borel. And then you want a G invariant function because the quotient by G is compact. The quotient by n is not compact. So you cannot use maximum principle. And in fact, there are solutions, right? So you should not forget that there are examples of Einstein manifold satisfying this, right? Any symmetric space fits into this picture. So it's not that we want to obtain a contradiction straight away. We want to see what happens, right? Now, how do we deal with these issues? Well, first of all, for issue 1, GIT comes into play. So there's a link between the Ricci curvature of solved manifolds and real geometric invariance theory. I don't want to say too many things about this, just to mention these words. And the fact is that to give you like a flavor of what this means, I mean, given any nilpotent Lie group, there exists some set of rational weights such that you have this estimate for the Ricci curvature of any left invariant metric on n. Okay, so you trace the Ricci, weighting it with these mysterious weights coming from geometric invariant theory. This comes from the Hesseling or K1S stratification, right? This is the label of the stratum where the Lie bracket lives in the representation of, you know, Lie algebra laws on n. But you get a curvature estimate, right? Which is non-trivial, and it's sharp on solitons. So this will play a role. I mean, unfortunately, I don't want to give too many details. There's many other remarkable properties satisfied by this mysterious set of weights. But the fact is that with this, with Christoph in previous work, we constructed a Lyapunov function for immortal homogeneous Ricci flow by looking at the volume density, which is, you know, the square root determinant of the matrix representing the metric in coordinates. But instead of taking the determinant, we take a weighted determinant. So imagine that Gij is diagonal. The determinant would be the product of Gii. But this is the determinant with weights given by this, you know, GIT theory. GIT, sorry. So we introduced this. It was crucial to construct the Lyapunov function. Somehow then we thought, okay, this is a function we need to consider, and then we need to obtain a nice PDE for this beta volume density, so to speak. It satisfies a nice PDE, but it's not greater than or equal to 0. So it doesn't give you anything straight away, right? You cannot apply the maximum principle to the PDE that we get here, right? So actually, to exploit this estimate, remember the problem was the curvature of the orbit. So we want to get rid of the curvature of the orbits using this estimate. So it's natural to try to consider adding these two functions, the one that I mentioned in the last slide and the GIT volume density, right? Now, the main problem is that when you include this one, then you get something which is not G invariant. And so it's not defined on the compact quotient, and you cannot use the maximum principle. So how to deal with that? Let me mention the last 5 minutes. The way we deal with that is the following. So Vn, the volume density of the orbits, is a gradient vector field, where the potential is the logarithm of, the mean curvature vector is a gradient vector field, where the potential is the logarithm of the volume density. Now, because n is a normal subgroup of G, the mean curvature vector happens to be G invariant. It's not only n invariant, but it's G invariant. But unfortunately, this potential is not. Right? If the gradient is G invariant, that doesn't imply that the potential is G invariant. So the idea is, well, you want the G invariant potential, right? But of course, You cannot change it. The difference will be a constant function, right? So what you do is you pay a price. I mean, you write H as the gradient of something where V is G invariant plus something else, you know? And you would like to say, well, let's say we do gradient plus divergence free, right? Like Helmholtz decomposition. But of course, this decomposition is unique. So if you do that, then you get that the divergence free part vanishes and you are back to where you started. So you need to impose some other condition on the remainder. And the condition we impose is that the divergence is a weighted divergence of H0 equals 0, right? So this is the divergence with respect to the measure weighted by V, e to the minus V times the Riemannian measure, okay? So that's why this, I mean, this is not how I thought about it. Of course, this is what the equations ask for. So you just do it and then there's some nice interpretation, but I don't have a clue why this is the correct thing to do. Now, the problem is, of course, you need to find a positive function. So you need to solve a PDE. It's a linear PDE. And well, let's not get into details. The fact is that you can find a positive solution to this PDE. And therefore you have your G invariant V. And at the end of the day, you consider the logarithm of the beta volume density plus log V plus something else. And this F satisfies a really nice differential inequality. And then you are done because you can apply the maximum principle on the compact manifold M mod G. The important thing is that this inequality came from using the Einstein equation. And for instance, in the process, we threw away the norm of A squared, right? So if you get equality, not only F is constant, but all the estimates that you use are sharp. So in particular, A is 0, namely the horizontal distribution is integral, right? And this is the first step, but it's of course the hardest one. Once you know something, then you can continue. So for instance, to prove that the n orbits are solitons, you choose this function, 1/2 the scalar curvature of the orbits plus logarithm of V beta, and this satisfies a nice differential inequality, blah, 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 rigidity. You get that the orbits are solitons. So perhaps I should try to explain how the theorem B implies theorem A. I more or less indicated, but the fact is, as soon as you get some non-trivial information, then, well, this is already a lot, right? But the precise way one can deduce theorem A is a bit involved. So I don't want to say too many things, just that you estimate the trace of the vertical Einstein equation, but without using what we talked about. Now you look at the Einstein equation, you remember that you were on a homogeneous space, and you look at the vertical Einstein equation using Killing fields. So it's going to be algebra, but also you want to use the rigidity that we obtained here. So somehow there's some estimates which using theorem B, one obtains a contradiction unless the Borel acts transitively. So in the case of a left invariant metric on a semi-simple Lie group, you always get a contradiction. There are no Einstein metrics which are left invariant. This is a bit mysterious, I know, but again, at the end of the day, you have to use homogeneity, of course, right? But for a moment, we had to forget about it, right? So maybe if I have 5 more minutes, are there any questions so far? Maybe I would like to finish by mentioning some open questions, which I find very interesting. So first of all, the first question is in the homogeneous setting in terms of the Ricci flow. So the Ricci flow is this weakly parabolic PDE for a curve of Riemannian metrics. And now an Einstein metric is a trivial solution to the Ricci flow. Namely, if you set up GT 1 plus 2T times G naught, then this solves Ricci flow. Okay. In particular, it does not only solve Ricci flow, it doesn't have any, it's a global solution to the Ricci flow. So it doesn't have any singularities in finite time, just by the fact that the Einstein constant is negative. On the sphere, the Ricci flow finishes in finite time, right? But on hyperbolic manifold, the manifold expands forever. So this is true for any negative Einstein manifold. Okay. So an Einstein manifold gives you an immortal solution to the Ricci flow. Now, one could phrase the Alexievsky conjecture as follows: that a homogeneous space which is not diffeomorphic to Rn has no invariant metric which is Einstein. This is a rephrasing of the conjecture. Okay. Now, our conjecture, which we call the dynamical Alexievsky conjecture, but this is not something Dmitry conjecture, just to make sure we're not misnaming it, is the fact that if the universal cover of your homogeneous space is not Euclidean space, then not only there are no Einstein metrics with negative Einstein constant, we claim there shouldn't be any homogeneous Ricci flow solutions which live forever. Okay, so an Einstein metric would be a trivial example of a solution that lives for all times. Some results in this direction, you should check out the poster by Roberto de Santana, who proved that this is indeed the case for a class of metrics on semi-simple Lie groups. And maybe the second open question that I wanted to mention is, in the case of principal bundles, which are Einstein, or more generally, when you have a non-transitive action, so M is an Einstein manifold with G acting isometrically, properly, co-compactly, then the claim is that M splits as a Riemannian product of the orbits, which will be homogeneous Einstein spaces, and a compact Einstein manifold, namely the base. And this has no symmetries because a compact Einstein manifold of negative Einstein constant has no continuous symmetry. So somehow the conjecture says that all the symmetries are contained in one of the factors and all the compactness is contained in the other factor. And about this, we have a recent result stating that this is true if the group is unimodular. But the non-unimodular case is unfortunately much harder. So yeah, perhaps this is a good time to stop. Thank you for your attention. Here's some references.